Python dictionaries, combining keys and values. Dictionaries let us store data using key-value pairs. They are like mini address books in Python. In this lesson, we will cover creating dictionaries, basic operations, common methods, real-world uses, and best practices. Running the cell now. We start by turning off Python warnings. Import numpy as np. We set the random seed to 42 for reproducibility. This makes our output cleaner. We create a dictionary named person. It has keys for a name and an age. Printing person shows both values together. Running the cell now. This output shows a simple dictionary with two key-value pairs, name linked to Thalys and age linked to 30. Notice how the keys are unique identifiers, and their associated values can be different data types. This example demonstrates the basic structure of dictionaries, which is foundational for storing and organizing data efficiently in Python. Dictionaries help us find information using a key. Here we ask for the name in person. Running the cell now. Here, accessing the value associated with the key's name in the dictionary person returns Alice. This illustrates how dictionaries allow quick lookups by key, demonstrating the core concept of key-value pairing we're focusing on in this lesson. If we look up a key that is not present, Python throws an error. We use try and except to prevent our program from crashing. Running the cell now. This output shows how Python handles attempts to access a dictionary key that doesn't exist, in this case, address, in the person dictionary. Instead of crashing with a key error, the code uses a try except block to catch the error and print a friendly message, demonstrating a best practice for safely working with dictionary keys. This is crucial for preventing runtime errors when keys might be missing. Syntax basics, creating and using dictionaries. Dictionaries are made using curly braces. Keys are separated from values with colons. Use a comma between key-value pairs. Running the cell now. We can also create dictionaries using the dict function. This example stores a username and a score. Printing user shows the key-value layout. Running the cell now. This output shows a dictionary created using the dict function with key-value pairs passed as arguments. Notice how the keys a username and a score are linked to their values of Bob and 42, respectively, demonstrating an alternative to using curly braces. This highlights that dictionaries can be created flexibly while still organizing data into clear key-value associations. Use the in keyword to check if a key exists in the dictionary. If the key is present, we can safely access it. Otherwise, we handle the missing key gracefully. Running the cell now. This output confirms that the key ledger exists in the person dictionary, which is important to avoid errors when accessing values. The lesson highlights the syntax for dictionaries and shows how to safely check for keys before using them, ensuring your code runs smoothly. Dictionaries let us update old values or add new keys. Here we update the age, then add a city. Now we see the updated dictionary. Running the cell now. Here, we updated the person dictionary by adding a new key-value pair, a city, London's, and changing the existing age of value to 31. Notice how the dictionary now contains 3 key-value pairs, demonstrating how to modify and expand dictionaries using assignment syntax. This reinforces the lesson on using colons for key-value separation and commas to separate pairs within curly braces. Use pop to remove a key and get its value. We take out the city from person and save it. Printing removed shows what was taken. We print person to check the result. Running the cell now. This output shows how the pop method removes the key of a city from the dictionary and returns its value, London. Notice that after popping, the original dictionary no longer contains that city key, which demonstrates how to both retrieve and delete a key-value pair in one step. This highlights an efficient way to modify dictionaries by key. Dictionary operations, getting keys and values. You can list all the keys, values, or both as pairs. This helps when you want to process or print everything. Running the cell now. This line is a comment explaining what the next lines do. This prints all the keys in the dictionary person. This prints all the values in the dictionary person. This prints all the key-value pairs in a person as tuples. Running the cell now. Here, the output shows the dictionary's keys, values, and key-value pairs, matching the lesson on dictionary operations. Notice how keys lists just the attribute names, values shows the corresponding data, and items combines both, which is useful for looping or processing all entries. This helps you understand the structure so you can access or manipulate dictionary data efficiently. You can loop through a dictionary using for. Each time, key holds the next key. Printing both the key and its value shows what is in person. Running the cell now. This output shows each key in the person dictionary paired with its corresponding value, demonstrating how to iterate over keys and access values. Notice the order reflects the dictionary's items, helping you process or print all entries efficiently, matching the lesson's goal of listing keys and their values. Using items is great for loops. It gives us both key and value at once. We print each part in a neat format. Running the cell now. This output shows each key-value pair in the person dictionary, printed line by line. Notice how items lets us access both keys and values directly, making it easy to process or display all entries in a clear, readable format. This demonstrates how dictionary iteration helps handle data efficiently. Useful dictionary methods. Get with a key and a default lets us avoid key errors. Update adds or changes many items together. Clear empties the dictionary completely. Running the cell now. Get lets us fetch a key with a backup value. If nickname is missing, we get our provided message. We see the result here. Running the cell now. The output no nickname shows how the get method safely retrieves a value from the dictionary without causing an error when the key is missing. Instead of raising a key error, it returns the provided default, demonstrating how get helps handle absent keys gracefully in your code. Update changes or add several key-value pairs simultaneously. Here we add a hobby and a pet. The new information appears in person. Running the cell now. Here, the update method adds multiple key-value pairs, hobby and a pet, to the existing person dictionary in one step. Notice how the original keys remain unchanged while the new items are seamlessly integrated, demonstrating how update simplifies expanding dictionaries efficiently. Use clear to empty a dictionary completely. Person is now blank and ready for new data. Running the cell now. Here, the clear method removes all entries from the person dictionary, resulting in an empty dictionary. This shows how clear effectively resets a dictionary, which is useful when you want to start fresh without creating a new variable. Notice the output confirms person now contains 0 key-value pairs. Real-world example, phone book. Imagine you want to store phone numbers. Dictionaries are great for contact lists. Running the cell now. Let us build a phone book with 3 people. Each name maps to a phone number. Printing contacts shows how easy it is to search. Running the cell now. This output shows a dictionary representing a simple phone book, where each name, key, maps directly to a phone number, value. Notice how dictionaries organize data for quick lookup, which is ideal for storing contacts as it lets you easily find a phone number by referencing a person's name. This demonstrates the core benefit of dictionaries in managing real-world, paired data. Let us let the user try searching for a name. We use input to ask for a name. The get method helps us avoid errors for missing contacts. The result tells us if we found the number. Running the cell now. Here, the output shows that when you type the name Eva, the program successfully retrieves and displays her phone number from the contacts dictionary. This demonstrates how dictionaries allow quick and easy lookups by key, which is perfect for implementing a phone book. Notice how the .get method also gracefully handles cases where a name might not be found, avoiding errors. Now let us allow adding a new contact. We prompt for the name and then the number. The new entry is added to contacts. We print the updated phone book. Running the cell now. This output shows the updated contact list stored in a dictionary, with names as keys and phone numbers as values. Notice how the dictionary now includes all existing entries plus the newly added contact from the user inputs. This demonstrates how dictionaries efficiently manage and update real-world data like a phone book. Let us practice removing a contact. The user types a name. Pop tries to remove and returns the number or none. If a number is found, we confirm removal. Otherwise, we show that the name was missing. We print the current contacts. Running the cell now. This output shows the successful removal of Bob from the contacts dictionary using the pop method with user input. Notice how the dictionary now excludes Bob's entry, leaving only Eva, Raj, and Lena, which demonstrates how dictionaries allow easy deletion of specific keys, perfect for managing a phone book dynamically. Mini project, counting words. Let us use a dictionary to count each word in a sentence. This technique helps with text analysis, like in chat apps. Running the cell now. This comment explains we are counting word frequencies. We ask the user to enter a full sentence. We split the sentence into a list of words. We create an empty dictionary to store word counts. We start a loop to process each word in the list. We check if the current word is already in the dictionary. If the word is present, we increase its count by 1. If the word is not present, we prepare to add it. We set the count for the new word to 1. We print out the dictionary showing word frequencies. Running the cell now. This output shows a dictionary where each word from the entered sentence is a key, and its value is the count of that word's occurrences. Notice how hellos appears twice, reflecting the code's logic that increments counts for repeated words. This confirms the intent of using a dictionary to efficiently track word frequencies in text analysis. We can sort the word counts by how often they appear. Sorted uses a special function to order from highest to lowest. Printing each word and its count shows the results clearly. Running the cell now. This output shows the words from the sentence sorted by their frequency, with hellos appearing twice and world and you'll appearing once each. Notice how the sorting highlights the most common word first, which is key for analyzing which words appear most frequently in text, a useful step in text processing tasks like chat analysis. Best practices with dictionaries. Descriptive keys make your dictionary more readable. Always check if a key exists to prevent errors. Use numbers or strings as keys, not lists or dictionaries. Running the cell now. You cannot use lists as keys because lists can change. Python will throw an error. Printing the error helps us remember this rule. Running the cell now. This output highlights a key lesson: dictionary keys must be immutable and hashable. The type error shows that using a list as a key raises an error, reinforcing why you should avoid mutable types like lists or dicts for keys. This ensures your dictionaries work as expected without runtime errors. Let us practice with a small challenge. We build a shopping cart dictionary. We add the number of apples. Bananas are added too. We add oranges and finally print the cart. This models how stores use dictionaries. Running the cell now. This output shows a shopping cart dictionary with clear, descriptive keys for each fruit and their quantities as values. Notice how using meaningful keys like bapels makes the dictionary easy to read and understand, aligning with best practices in dictionary design. This approach helps avoid confusion and errors when accessing or updating items later. Now let us add up all the fruits. We set total to 0 at first. We loop through every quantity in the cart. We add each to total as we go. We print the final total. Running the cell now. This output shows the total count of fruits in the cart dictionary by summing all the values, which represent the quantity of each fruit. Notice how the code iterates over the dictionary's .values to aggregate counts cleanly, demonstrating a clear and readable approach to working with dictionary data. This reinforces the lesson's intent to use descriptive keys and straightforward methods to access and process dictionary contents effectively. Let us let the user search for a fruit count. We use input to ask for a fruit name. Get returns the matching value or 0 if it is missing. We print the result for the fruit. Running the cell now. This output shows the count of the requested fruit, apples, retrieved from the cart dictionary using the .get method. Notice how using .get, with a default of 0 safely handles the case where the fruit might not be in the cart, avoiding errors. This reinforces the best practice of checking for missing keys gracefully when working with dictionaries. Sometimes, we want to remove an item that might not be present. We check if raspberries are in the cart first. If so, we remove them safely. Otherwise, we print a message. Running the cell now. This output shows the code safely checking for the raspberries key before trying to remove it, reflecting the best practice of avoiding errors by verifying key presence within. Since raspberries wasn't found, it prints a clear message instead of throwing an error, demonstrating how to handle missing keys gracefully. Recap. Dictionaries store and organize data using keys and values. You can add, look up, modify, and remove entries easily. Their flexible structure is great for many types of projects. Running the cell now. Fromkeys is a handy shortcut. We make a dictionary where each key starts with the same value. Printing nums shows how fromkeys works. Running the cell now. This output shows a dictionary created using fromkeys, where each key from the list has been assigned the same initial value, 0. Notice how this method quickly sets up multiple keys with a default value, demonstrating an efficient way to initialize dictionaries before modifying or updating them later. This ties into the lesson on how dictionaries can be easily created and organized for various uses. You can make a copy of a dictionary using copy. Copy_cart is a new object, so changing cart later does not change copy_cart. Printing shows the copy matches the original. Running the cell now. This output shows a copied dictionary identical to the original cart, containing keys for fruits and their quantities as values. Notice how the .copy method creates a new dictionary with the same key value pairs, allowing you to work with duplicates without altering the original. This reinforces the flexibility of dictionaries for safely managing and organizing data. Try it yourself. Short challenge tasks. Make a dictionary called Book with keys title, author, and year. Update the year. Remove the author. Print the final book dictionary. Running the cell now. Here is an example of how you could solve the challenge. We create the book dictionary. We update the year value. We remove the author from the dictionary. We print the resulting book. Running the cell now. The output shows the final state of the book dictionary after updating the year from 2020 to 2024 and removing the author key. Notice that only the titles and updated a year remain, demonstrating how to modify and delete key value pairs as intended in this short challenge. Final thoughts and next steps. You have learned the basics and some extras of Python dictionaries. Practice with different kinds of data. Like and subscribe for more Python lessons. Running the cell now.